Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome to Lecture 2. Now, before we dive into the physics of transistors, what I want to do is to spend 2 lectures reviewing some basic concepts of semiconductors and semiconductor physics. Now, many of you have an extensive background in semiconductors, and this will be pretty familiar to you. Some of you don't have much background in semiconductors, and it's going to go pretty fast. Now, what I mainly want to do is just highlight the concepts that we're going to be using for the rest of the course. If you can get comfortable with using those concepts, you'll be set for the rest of the course. And the references give you some pointers to additional resources if you'd like to fill in your gaps. So we have 2 parts of this lecture. Part 1, we'll just dive right into it. And we'll go back and begin with basic freshman chemistry. So you remember that atoms have energy levels. And silicon is an atom that has atomic number 14, so it has 14 electrons. Those 14 electrons have to fill into these energy levels. N equals 1, 2, 3, 4, etc. And we just start filling up the energy levels from the lowest energy until we've accounted for all 14 electrons. And in order to do that, we end up filling up some of the N equals 3 energy levels. The two S levels are completely filled, and then there are 6 states in the P level, and we only need 2 of those, and we've accounted for all 14 of the electrons that we need to. So deep down, low in energies, we call those the core levels. We don't need to worry much about them because there's not much that we can do to affect them. But the highest energy levels are the ones that we worry about because we can manipulate those, and they're involved in chemical bonding, and those are the energy levels that we make use of in electronic devices. And the important point is that in the highest most energy levels, we have 4 electrons, 4 valence electrons, but we have 8 states there, so there are 4 empty states as well. Now, we're going to be primarily talking about transistors made on silicon. So think about a chunk of silicon. It has a lot of silicon atoms arranged in a regular lattice, 5 times 10 to the 22nd of them per cubic centimeter. And they're arranged in this diamond lattice. Each silicon atom has 4 nearest neighbors, and the lattice spacing here is about 5.5 angstroms. Now, something different happens when we put silicon in a lattice and it can bond with its nearest neighbors. Those energy levels change, and we're going to need to discuss how they change. Important points to make is that we're only interested in the topmost energy levels, the valence states. There are 8 of those, so that gives rise to 8 times Na states that we'll be interested in. But the interaction of the electrons' wave functions as they interact with their neighbors changes the energy levels, and that leads to what we call energy bands. So the energy levels become energy bands. The 3s states and the 4s states couple and merge, and we end up with the same total number of states. We don't simply have 5 times 10 to the 22nd of these energy levels. They interact and the states become bands. We have half of the states end up creating a band of states where there are energy levels so finely spaced that we consider them to be continuous. But 4 times Na of those states are in the lower band. 4 times Na of the states are in the upper band. All of the states, all of the electrons then can be accommodated in the lower sets of states, and there's a gap in energy, and all of the states above are completely empty. We call that gap the forbidden gap because there are no states there. Electrons can't be inside that gap. That's what happens at temperature equals 0. If we have a room temperature, we have a little bit of thermal energy. We can move an electron from a lower state to a higher state. So we have a few empty states in the bottom set of bands, in the bottom band, the valence band, and we have a few electrons in the conduction band, which was empty at T equals 0. Okay, so that allows us to explain what makes an insulator, what makes a semiconductor, and what makes a metal. So an insulator is just a material that has a very big band gap. So consider silicon dioxide, for example, the insulator that's used as the gate insulator in most MOSFETs. It has a band gap of 9 electron volts. The thermal energy is kT, and that's roughly 0.026 electron volts. So there isn't very much thermal energy, not nearly enough to break a bond and to move an electron from the valence band to the conduction band. So we don't have any electrons to conduct electricity, and the material is an insulator. Now, a metal is completely different. In a metal, it ends up that the states within one single band are filled only halfway into the band. So we have filled states and empty states, and the electrons now are free to move. If we apply a voltage, give them a little bit of energy, they can just move up and fill one of the empty states, and current will flow. Now, a semiconductor is like an insulator. It just has a smaller band gap. And it's small enough that we can break a few of these bonds, and at reasonable temperatures, we can create some empty states in the valence band, and we can create some electrons in the conduction band. So that's a material then that we would call a semiconductor. The band gap of silicon is 1.1 electron volts. The band gap of a good insulator like silicon dioxide is 9 electron volts. Okay, now let's look a little more carefully. Within these band of conduction band states and valence band states, we have all of the states distributed between a bottom energy and a top energy. And in the valence band, a top energy and a bottom energy. And they're distributed in some way throughout that energy range, and we call that the density of states. It's the number of states per unit energy, typically per unit volume. Okay, so there's one for the conduction band, one for the valence band. So these states are very finely spaced in energy. You know, they came from those original atomic energy levels, but they're smeared out and they're spaced so finely that we just consider this to be a continuous distribution of states. If I integrate over all of those energy range from the bottom to the top, I'll just find the total number of states. So half of the states associated with that n sub a, 5 times 10 to the 22nd atoms, are located in the conduction band. The other half are located in the valence band. And it's important to realize that these states are extended in space. If an electron is in a silicon energy level of an isolated silicon atom, it's physically in a particular region, not free to move throughout space. Inside a silicon crystal, these states are extended, which means the electrons are free to move throughout the crystal. The holes are actually free to move throughout the crystal also, and we think of them as positive charge carriers. Okay, now we're only going to be able to perturb things. We're only going to be able to make a few empty states near the top of the valence band and a few filled states near the bottom of the conduction band. So we're really only interested in what happens near the edges of these bands. And near the edges of these bands, turns out that they have, for typical semiconductors, they have a simple shape. They tend to go parabolically with energy. And then those of you that have had some semiconductor physics courses will have derived the density of states in this region near the bottom of the conduction band. And you might remember that it goes as the square root of the energy with respect to the bottom of the band. And there are parameters called effective mass that come from that material properties as well. We have a similar expression for the valence band. The number of states in the valence band goes as the square root of the energy difference between the energy and the top of the valence band. So these are typical expressions that we will use. They assume common simple energy bands that we call parabolic energy bands. Okay, but you should remember that, you know, the particular shape of the bands depends on details of the band structure and depends on whether the material is a 1D, 2D, or 3D material. Okay, now I want to talk about something else we'll call an energy band diagram. We're going to be spending a lot of time looking at energy band diagrams. And what do we mean by energy band diagram? So the electrons are delocalized and free to move. The holes are too. And that means everything is happening near the band edges where we know the densities of states. So it's very useful to plot the conduction band versus position and the valence band versus position, and then we can get an intuitive feel for how the electrons and holes are moving throughout the silicon crystal. Okay. All right, now, another important concept that you've seen before in semiconductor physics and we'll be making extensive use of is this Fermi function. So we know that typically in the valence band, the states are mostly filled. In the conduction band, they're mostly empty. If I were to make a plot of the probability that a state is occupied, probability goes from 0 to 1. And I know that the high energy states have a small probability and the low energy states have a high probability, so I could just sketch what it should look like. And I know that way below the valence band, the probability is 1. Way above the conduction band bottom, the probability is 0. And it makes a transition that's something like that. Now, it turns out that there is a key parameter we'll call the Fermi level. And the Fermi level is the energy at which the probability of a state being occupied is 1/2. Here I've drawn it in the forbidden gap for which there are no states. If there were a state there, it would have probability 1/2 to be occupied, but there are no states there, so there can be no electrons there. Okay. So there's a small probability of the states at the top of the valence band of being empty because the probability is not quite 1. And there is a small probability of states near the bottom of the conduction band of being filled because the probability is not 0. And that particular function is well known. It's has a simple mathematical form. It's called the Fermi function. And it simply gives us the probability that a state at a particular energy with respect to the Fermi energy is occupied. Okay, so now we can sketch what we would call an N-type semiconductor. In an N-type semiconductor, there are a few electrons in the conduction band that are free to move. And in an N-type semiconductor, that means that the Fermi level would be up closer to the conduction band, such that there's some small probability that those states near the edge of the conduction band will be occupied. We could sketch a P-type semiconductor. So here's an energy band diagram, energy versus position for the valence band and the conduction band. We'll sketch the Fermi energy. We'll put it down near the valence band now. Because if I do that, there's some small probability that the states near the top of the valence band are not occupied, which will give me an empty state or a hole that is free to move around and act like a positive charge carrier. Now this Fermi level is very interesting because I can now put the Fermi level and the densities of states together and I can relate them to the density of electrons or holes. So if I want to know what is the density of electrons per cubic centimeter in the conduction band, well, it's the number of states per cubic centimeter, which is the density of states in that energy range times the width of that energy range, times the probability that the state is occupied, which is given by the Fermi function. And then I integrate from the top of from the bottom of the conduction band. I should integrate to the top, but I'll take the integration all the way to infinity because the Fermi function will make the probability go to 0 anyway, so I'll never get to the top. Well, you just plug in our expressions for the Fermi function and for the densities of states, and we do the integration, and we can find an answer. So it takes a little bit of math. Let me do it quickly, and you'll see how that works on one of the homework problems for yourself. Here's the Fermi function, here's the density of states, this is the integral that we need to do. Okay, I'll move all of the constants out front, so I have an integral like this to do. I'll define some parameters. Eta is a normalized energy. It is the energy with respect to the bottom of the conduction band in units of kT. And eta F is a normalized Fermi energy. It's the Fermi energy with respect to the bottom of the conduction band in units of kT. And then I'll do a change of variables and I'll convert my integral to this form. Now I have an integral that if I can work out, we have an answer. Okay. So I'll lump all of the constants together and I'll call them n sub c. That's something that we call an effective density of states. It involves things like effective masses and kTs and is a material dependent parameter. So that's something that is known for any common semiconductor. We'll call it the effective density of states as units of per number of states per cubic centimeter. Okay, so if we do that integral, it turns out you can't do that integral. You can always do it numerically on a computer, so we'll just give it a name. And the name we give it is Fermi-Dirac integral of order 1/2. The 1/2 comes because we had the normalized energy to the 1/2 power, and we have a normalizing fraction out here. It's just a name that we give to this particular function. The only way we can evaluate that is to integrate it with Simpson's rule or whatever numerically, because there's no analytical solution for that integral. But that doesn't matter. We can evaluate it numerically. So the electron density is related to the effective densities of states, which involves material-dependent parameters like effective masses, and it's related to the position of the Fermi energy with respect to the conduction band edge. Okay. So we have the expression. Now, Fermi-Dirac integrals make things a little bit complicated mathematically. We're going to try to avoid them for the most part in this course, but there will be a time or two when we'll need to use them. So I want to just mention something about Fermi-Dirac integrals and then point you to some notes that you can find on the nanoHUB that will tell you all you need to know about Fermi-Dirac integrals to solve common semiconductor problems. This is the definition of the general Fermi-Dirac integral. The normalizing factor out front, the square root of pi over 2 that we saw, is in general 1 over the gamma function of argument j plus 1. You know, we dealt in the previous slide with a j of 1/2, but in general j could be an integer or any half integer. So these are some useful parameters. The gamma function, remember, is something like a factorial, and there's a recurrence relation that allows us to determine it at one value if we know it at a value that is just one integer away. There are some nice properties such that if we differentiate it, we just kick the order down 1. And the Fermi-Dirac integrals also simplify greatly. When this parameter eta f is much less than 1, much less than 0 actually, where the Fermi level is way below the bottom of the conduction band, then the Fermi-Dirac integrals of any order just reduce to an exponential. And that makes things simple, and that's mostly the way we're going to be using them in this course. Okay, now be sure when you're dealing with Fermi-Dirac integrals that you don't confuse this. When you're reading papers, you might come across papers that talk about a Fermi-Dirac integral that's defined a little differently. And usually this will be written as a Roman F instead of as a script F. The Roman F doesn't have this normalization factor out front. And you have to be careful about that. That normalization factor is very nice. It allows us to differentiate Fermi-Dirac integrals and use this simple expression. But people do it both ways, and you have to be careful to know how they're doing it. Okay. So if we make this assumption that the Fermi level is way below the bottom of the conduction band, then that Fermi-Dirac integral simplifies to an exponential. And under those cases, we'll get some very simple expressions. The Fermi-Dirac integral becomes an exponential. Eta f is just the Fermi energy minus the bottom of the conduction band in units of kT. So we get a very simple expression that just says that the electron density is exponentially related to the distance between the bottom of the conduction band and the Fermi energy. Higher the Fermi energy, the more the electron density is. So this assumption would be called non-degenerate carrier statistics or Boltzmann carrier statistics. Makes life simple. We will use it frequently. Every now and then when we need to be more accurate, when we're analyzing experiments, then we'll resort to Fermi-Dirac integrals. Now you can do the same thing with holes. The Fermi energy here is near the conduction band, so we have a significant number of electrons in the conduction band, but there are a few holes, and the separation between the Fermi level and the top of the valence band determines how many. And you can go through the same kind of argument, and you can relate the hole density to the Fermi energy with a Fermi-Dirac integral. There's an effective density of states that involves the whole effective mass, and the parameter eta f now is the difference between the top of the valence band and the Fermi energy. Okay, and I can simplify the whole expression for Boltzmann statistics as well. You know, then if I look under equilibrium conditions, and if I take my simplified expression for the electron density, my expression for the hole density, and if I multiply them the two together, I get this. And it turns out then that the Fermi energies drop out. So the result is independent of the Fermi energy, and the result just depends in the end on the difference between the conduction band and the valence band. That's the width of the forbidden gap, and on these two material-dependent parameters, NC and NV, which depend on the effective mass for electrons and holes. So the product of N and P we'll call Ni squared. And in an intrinsic semiconductor, we have an equal number of electrons and an equal number of holes, and that number is given by this simple expression. And silicon, it works out beautifully. Room temperature in silicon, the intrinsic density of electrons or holes is almost exactly equal to 10 to the 10th per cubic centimeter. That's a very small number. Remember, there are 5 times 10 to the 22nd silicon atoms per cubic centimeter. Okay, just a couple more things and then we'll wrap up. We can make semiconductor devices because of doping, and that's what makes semiconductors so useful. We can change the number of electrons in the conduction band or the number of holes in the valence band by controlling the location of the Fermi energy and doing that by doping. And this is how it works. Here's my silicon lattice, a little cartoon picture. Each silicon atom has 4 valence electrons and 4 nearest neighbors. So when you put these all together with their 4 nearest neighbors, they have a completely filled shell, 8 electrons. And that's covalent bonding that makes the silicon crystal. But if I substitute, say, a phosphorus atom from column 5 of the periodic table, it has 1 extra electron. So it goes in to the lattice where it's supposed to, but there's 1 electron left over. Or if I substitute a boron atom, column 3, it has 1 too few electrons. So it goes in, but there's a missing bond in one place. Now if I look at the electrons, it takes just a little bit of energy to break that bond and put that electron in the conduction band and let it flow throughout the crystal. So we would draw that energy state of that 5th electron just below the conduction band, and at room temperature, that electron bond would be broken and the electrons would be up here in the conduction band. We would say that we've doped the semiconductor N-type. Now, if I look at this boron atom, it takes just a little bit of energy to break the next bond and put it over here and fill that missing bond. Now I've created a hole that's free to move around through the semiconductor crystal, so I've doped the semiconductor P-type. And that little energy I would draw down near the valence band. Okay. So this is what we mean by N-type and P-type doping. We dope N-type to make the source and drain on an N-channel MOSFET. We dope P-type to make the source and the drain on a P-channel MOSFET. All right. So we have these densities of dopants. At room temperature, most of those dopants are ionized. You know, the 5th electron has been released to the semiconductor crystal, or in the case of the boron atom, another electron has filled that bond. Okay, and then finally we can talk about how we would in general determine the number of carriers in the semiconductor. And we would do it this way. Semiconductor likes to be neutral. So if I look at the charge density in coulombs per cubic centimeter, it's charge at an electron times the positive dense contribution from the holes minus the negative contribution from the electrons plus the positive contributions from the dopants. So it's positively charged once that 5th electron is broken off, minus the negatively charged acceptors. And electrons and holes will flow around and try to make everything neutral. Okay. So if I try to solve that expression, if I assume that all of the dopants are ionized, then I can assume this is just the density of phosphorus atoms and the density of boron atoms. And now I know that the product of N and P is Ni squared, so I could eliminate P, and I'll get a quadratic equation for N. And you could do the algebra, and what you'll find is that near room temperature, the number of electrons in the conduction band is very nearly the number of phosphorus atoms that you put into the silicon crystal. And the number of holes in the valence band is very nearly the number of boron atoms that you put in the semiconductor crystal. So it makes it very easy for us to control the density of electrons in the conduction band and holes in the valence band. Okay, so That's it for the first half of this review of semiconductor fundamentals. The key points that I want to leave you with are the importance of this density of states, which describes how the energy levels are distributed in the conduction band and the valence band. The fact that the Fermi level is a critical energy level that determines the probability that those states are occupied. The fact that we can mathematically relate the carrier densities to the location of that Fermi level. And the fact that what makes semiconductors so useful is that we can control by doping the location of the Fermi level and move it from anywhere down near the valence band to up near the conduction band edge. Okay, so that's part one of the review. We'll continue the review in the next lecture, and then we'll be ready to dive into MOSFETs. Thank you.